plan is to give a brief overview of various integrable systems that can be seen. I think you need to turn on the sound. Should be set up. Brief overview, because obviously many of those things will be covered in depth by other speakers. For example, Anton, of course, will be talking about the KdV equation in details, but I think he will not address this particular point of view which I'm going to present. And I'm also going to show some of the results which center on the notion of Banach-Poisson space, which is central in our approach. And to finish, maybe I will present some of the results we obtained with Professor Odzijewicz and Barbara Tumpach recently. So the first example that I know are the papers by Sato and Segal-Wilson, which were able to give a more rigorous analytic approach to solvability of KdV equation using the restricted Grassmannian, which led to this restricted Grassmannian is an infinite-dimensional manifold modeled on a Hilbert spaces, and it's useful in many other parts of mathematics. It's loop groups, of course, to other soliton equations, also to field theories, including fermionic second quantization. The other part of the talk will be related to some generalization of quantum mechanics in the sense of Hamiltonian mechanics, which started with a paper by Pavel Bona, and then papers by Odzijewicz and A.B, and some other papers which explored the possible generalization of the notion of Poisson manifold in infinite-dimensional spaces. There's a lot of more of them. Last week, Barbara was giving more detailed overview of the subject. We have a review paper which is going to appear in the proceedings. It's already on archive if anyone is interested, together with Praful. There are some more papers, but maybe I won't waste time. So the plan is like this. I start with the description, what is the restricted Grassmannian and how it relates to the KdV equation. And after doing that, I will speak a bit more what are Lie-Poisson spaces, and give some example of them. Some of them will be related to quantum mechanics. The other will be related to semi-infinite Toda-lattice. And to finish, I will return to the restricted Grassmannian and show some Lie-Poisson spaces which are related to them, which lead also to some integrable system which can be also realized in some special case on the groupoid of partial isometries. One of the examples of groupoid in a Banach setting. Last week, if you were there, there was a talk, mini course about it by Aneta Zizewska. Okay, so to start with the Grassmannian, we need to have a separable Hilbert space. We fix an orthogonal decomposition of this space into two infinite-dimensional subspaces by P plus and P minus I denote projectors onto those components. And the restricted Grassmannian is just a set of those Hilbert subspaces which projected to W, when P plus restricted to W is a Fredholm operator, so it means that it's an invertible modulo compact operator, or equivalently that its image of its kernel and image of dimension of orthogonal complement of image is also finite dimensional, and P plus, P minus restricted to W is a Hilbert-Schmidt. It's more, I will be using a different characterization of the restricted Grassmannian soon, but let me just say that it's a very standard example of a symplectic manifold in a Banach context. It's actually a Hilbert manifold with a symplectic form, which is given by cocycle, which is called Schwinger term, which comes from as I said, so from field theory. And in the idea to get the atlas on the Grassmannian is the usual one which everybody uses to give an atlas on any Grassmannian space. Take a Banach space of Banach space and have a Grassmannian of split subspaces, and that's exactly the way you define a manifold structure. So you just take graphs of an operators, and those graphs under certain conditions belong to the restricted Grassmannian. So it's possible to write down the formulas explicitly, since only an introduction, so I'm not going to give the formulas in detail. They were presented actually last week, but that's helpful for those who are not here. Anyway, the connected components are indexed by a threshold index of the operator P plus restricted to W. So this is the operator here. So it's the difference of dimension of kernel and orthogonal complement of image. And now to any operator on a Hilbert space with polarization can be given in a block form with respect to direct sum. So we have A++, which is operator from A plus to A plus, and so on. So the natural object which appears immediately is a certain Banach Lie group, group of invertible operators such that of codiagonal blocks are Hilbert-Schmidt, and automatically then the other blocks are Fredholm. It follows from the definition. Or its counterpart, the unitary group, is also interesting. It turns out that Grassmannian is actually Grassmannian is homogeneous space with respect to the action of this group on the Hilbert space. We start, for example, from H plus, and the orbit is a Grassmannian, so we can give it a structure of a homogeneous manifold. In the easiest case, for example, unitary is a bit easier. We can identify it with a quotient of the unitary restricted group by the unitary operators acting in H plus times unitary operators acting in H minus. Okay, so yes, it's written. So the essential case which is useful for the description of the KdV equation is when we take as H as Hilbert space of complex square integrable functions on the unit circle, and you can take functions which extend holomorphically into the interior of the circle or to the outside of the circle. It turns out, I'm skipping all the details now, so it's a very rough presentation of what's really going on for the KdV. So if you have a function, then multiplication by this function can happen to belong to GLRS, and for example, it happens if this function is twice differentiable. So one can consider a group of operators of this form, which we denote by gamma. It has subgroups which are related to this decomposition, so the functions tend to inside and the outside of the disk. Now the Korteweg-de Vries equation, which we saw yesterday during the first lecture by Anton, looks like this, and the idea behind the construction is that solutions to KdV will be realized as a flow on some part of the restricted Grassmannian. The trick is that we take a subset of the restricted Grassmannian given by subspaces W such that multiplication by Zn, a particular representation of a Grassmannian. So we have this acts as a shift operator on the basis, and we take elements of the restricted group in this form with almost all t equal to 0. Idea is that we can construct a function starting from an element of a Grassmannian, a certain function which will flow accordingly to KdV equation when we use this element of a group on W. So flow on the KdV equation will be realized on the restricted Grassmannian by elements like this. The definition of this function is not very straightforward, and again, suppress all the necessary detail. It's related to so-called tau function of the yes. What?
It's L2 space of functions.
Yes, L2 space on a circle.
L2 space on a circle.
Yeah, L2 space on a circle. So it's this function which appears here is, in a certain sense, the determinant of some operator which appears in the theory of restricted Grassmannian. That's the broad idea. Maybe after Anton talks, I could be able to give more details, but now I think I will just have to undermine his plan for his talk if I would have to explain more details. So I'll switch on to the Poisson spaces. So it's a known situation in finite dimensional case that a dual of the Lie algebra carries a natural Poisson structure, which turns out to be not exactly true in finite dimensions. And moreover, there are many other problems which are attached to the notion of Poisson manifold, even in a simplest context, Banach manifolds or even Banach spaces. What I wrote here as a definition of Banach Poisson manifold is a definition given by Odzijewicz and A.B with some clarification that we made with Tita and Barbara Tumpach later on, which I'll comment on in a minute. So we need to assume that the Poisson bracket is given by a Poisson tensor. It's no longer automatic. You were told yesterday that it is automatic, that if you have a Poisson bracket which satisfies 4 conditions, of Anton and Oskar gave these conditions. We have bilinearity, antisymmetry, Jacobi identity, and Leibniz identity, and they no longer imply that Poisson bracket is defined by some bivector field or some Poisson tensor on the differential of the function. Actually, it follows from an observation which can be found in Michael Kriegel's book about realization of vector fields on the infinite-dimensional manifold. Not every derivation on a function, on the germs of function on the manifold is realized by actual tangent vector defined as an equivalence class of curves. So there are so-called kinematic tangent vectors which are given by curves on the manifold, and operational tangent vectors which are given by derivations. There is a lot more of those derivations, even if manifold in question is just a Hilbert space. There are, for example, derivations which depend on the second derivatives of functions. Actually, it's not only a phenomenon appearing in infinite dimension, it can also appear in a very simple finite dimensional manifolds like R. If you consider R real line as a manifold of a class Ck, not C infinity, but Ck, you also get many more derivation on a class of function than one-dimensional space. So it's actually an infinite dimensional space of derivation in this case. 50s or 60s already. So for the definition of Banach Poisson manifold, we need to assume that the Poisson tensor exists, which is not automatic. And this Poisson tensor is in general a smooth section of some bundle which is double dual to the tangent bundle in infinite dimension. Again, it's not always the same as a tangent bundle. So another problem arises that Hamiltonian vector fields might not exist. Either a sharp map, which was yesterday, the inverse of this map was written, but this map was also written point. This map doesn't take values in the tangent space, but only in its double dual, which is larger in general. So the Hamiltonian vector fields would no longer be really a vector fields unless we put an additional condition, and that's what Odzijewicz and A.B did. They assumed that this sharp map indeed takes values in a tangent bundle. That's not the only possible solution. There are many other approaches to Poisson brackets. As I said, there are approaches also by Karl Hermann Neb, by Fernand Pelletier and Daniel Beltita, and of course Barbara Tumpach, who try to generalize this approach to Poisson brackets, which are not defined for all smooth functions, but only on some subclass defined one or the other way. I'm not going to talk about these details because it was already discussed last week. So one thing that I still need to comment is that assumption of localizability is usually required for those notion of Poisson bracket, because on manifolds in this context, there may not be a bump function, smooth bump function, so it's not possible to conclude in general that the Poisson bracket is, yes? Oh, there are more probably. We just consider as bilinear maps on T star taking values they should. Yes. Bilinear maps. Since we don't have smooth function with compact support, even on LP spaces for certain values of P, it's not possible to conclude that Poisson bracket in general would define only on the local behavior of the functions. So one needs to plug in the localizability into most of the definitions. Otherwise, one can have problems down the way. Even if one uses objects like something like this Poisson tensor of sharp map, it may happen that you lose some properties when you move on to the local function. So is quite subtle in this point, and that already discussed that there are some Poisson brackets which are not defined by a Poisson tensor. Moreover, one of the problems which we suspected that there exists but couldn't really solve one way or the other is that we are not certain that if you take all smooth function of the manifold and consider the derivatives, differential of these functions at a certain point, that they will span the whole cotangent bundle, cotangent space at this very point. Finite dimension, you do it using bump functions. You take a map which are linear in the chart, you just move them to the manifold, and you can show that you can get any cotangent vector as a differential of globally defined function in infinite dimension. Wouldn't that mean another definition of tangent bundle? Yes, of course. That's because there are also a sheaf of Poisson brackets, and that's an approach, of course. Anyway, the problem is that if we only work for globally defined vector function, Poisson tensor may not be unique. Okay. So now let's go to the situation which happens when we want to consider a dual of Lie algebra. It turns out again that the dual is not a correct object to endow with a Poisson structure, and the better object is a predual space. So Banach-Lie Poisson space is a Banach space such that each dual has a structure of Lie algebra. Now it's written with a Poisson bracket, but you can see it the other way around. We have a Banach space B, and its dual is a Banach-Lie algebra satisfying this property. Then it means that we have a Lie Poisson bracket defined on it with the usual formula, finite dimensional case. So we have, in other words, we have a predual of a Lie algebra. We have functions on this predual. The derivatives at a certain point can be seen as an element of the Lie algebra that it's possible to take a commutator. If we were to assuming there is a predual, yes, of course, it's not given. Yeah, I mean, there are classes of equation where you have those, like for Neumann algebras, but I don't know if there is a condition. We do with respect to topology, bracket, I'm not sure. Anyway, if you would take here G star, then you would have the differentials which will be G double dual, which would not have a which do not have a algebra structure, so this formula will not make sense. Put on the previous slide, additional condition is necessary to ensure the existence of Hamiltonian vector fields. The Hamiltonian vector fields. So the model example is, of course, the space of trace class operators on a Hilbert space. It is a predual space to the space of bounded operators, which is a particular case of what I said about von Neumann algebras. For every von Neumann algebra, it can be done. It was the main example described in Odzijewicz and A.B. paper, but this example is crucial, for example, for quantum mechanics. L1 is a space of density matrices, only it, for example. So we have, since L1 is an ideal, that the formula with add star is satisfied, add star preserves the predual, and we can write down the Hamilton equation. This is a particular case where differential of h, if h is a linear function, then this differential is just an operator, so we get version of Liouville of von Neumann equation for which is in this context just a Hamilton equation on the Poisson manifold L1. And since we are in Schrödinger Institute, of course, if rho is taken as a rank 1 operator, we get equation or the generalization of it. The other example from another paper by Odzijewicz and A.B. is that we can consider a weak symplectic manifold of bounded sequences and summable sequences and introduce a symplectic form on those. It's a weak symplectic form, so it doesn't give us a Poisson bracket in the sense I described, but it gives us some weaker Poisson structure. And one can write a Hamiltonian which describes the dynamics of Toda-lattice. In this paper, much more results were obtained about semi-infinite Toda-lattice. For example, there is a momentum map which takes values in L1. Now we have kind of a Poisson structure here, some Banach Poisson structure here. So it's possible to consider this as Poisson map. In fact, this paper, when I was looking at it yesterday, I noticed the acknowledgement. It's written that the work on this paper started exactly in the Schrödinger Institute many years ago. So the authors put it in acknowledgement. Okay, so I'm slowly running out of time. I'll just give a bit of information about predual Lie-Poisson spaces which are related to restricted Grassmannian. We had this unitary restricted algebra, which in block form consisted of unitary operators which had L2 operators here. And here was something, there were operators of this form, and it was proven by Beltita, Ratio, and Tumpach that there exists a predual space to this space. In this form, we need to replace those star by L1 operators. So L1, L2, L2, L1. Predual space of this unitary restricted algebra. And again, since L1 and L2 are ideals, adjoint action preserves the predual, so everything goes smoothly. You can define a pairing using a trace. It's a bit tricky. You could not write the usual trace because it would not converge in general, since product of this thing and this thing is not a trace class operator. But if you restrict it to this block diagonal, it is. That's why we have a formula which looks a bit stupid, but it's not. It's required to make the formula converge. Restricted trace is, again, something that does not behave as the usual trace in all cases. Not all operations are permitted, so one has to be careful. For example, for this Poisson structure, we were able to find a family of functions in involutions, which gives some example of integrable system. And now we come back to the notion of integrability, which I'm not going to rigorously define. Yesterday we heard some definitions about Liouville-Arnold notion of integrability. You have to have proper number of integrals of motion. Well, in infinite dimension, this proper number is infinity, and you never know if you have enough, because there are, to remove some of them, you still have infinity, but maybe it's not enough. Maybe you need to add something more. However, many authors use the very relaxed definition of integrable systems in infinite dimension. They assume that if you have an infinite family of commuting functions, then you say you have integrable systems. However, in the case that I wanted to describe, but I won't since I'm running out of time, you can write down some solution in particular case. You can write down the momentum map, you can write down some solutions, you can write down realize restricted Grassmannian there, and even move it to the groupoid of partial isometries. So have some dynamics on the space of partial isometries of a Hilbert space. I think I will need to stop right now.